Welcome to a class on Advanced Mathematical Method 1. Today, we shall be looking at an interesting topic, part of Special Differential Equation, and the topic is Hypergeometric Equation. What is the significance of Hypergeometric Equation? Like I said earlier, it is one of the so-called special functions, special equation as far as mathematics is concerned. What makes it special, or what makes those that we call special equations special? Number one, they have special structures. Number two, their solutions are often used as tool to solving some other applied problem. So today our focus is on hypergeometric equation. How does it look like? How can we determine the solution to hypergeometric equation? That will be the focus of today's class. Once again, you are welcome. A second order ordinary differential equation of the form x into 1 minus x y prime prime plus c minus r plus s plus 1 x y prime minus r s y equals to 0, call it equation 1. This equation 1 is what referred to as hypergeometric equation. So equation 1 is called hypergeometric equation. That is what we have. Now, it should be noted that equation 1, we need to note that equation 1 has initial roots 0 and 1 minus t. After solving at regular singular point using the method of Frobenius. If we use the method of Frobenius, we are going to obtain two roots that are called initial root, and those two roots are 0 and 1 minus t. 2. After substituting for each value of the initial root, we are going to generate two solutions that are linearly independent. And those two solutions are y1 equals summation r sub k s sub k divided by t sub k, k factorial, x raised to the power k from 0 to infinity, which is otherwise known as hypergeometric function. And it can be written in that form as r, s semicolon t semicolon x. That is the solution that we are going to have after solving using Frobenius to obtain the initial root 0 and 1 minus t, and by the time we substitute the initial root 0 into the recurrent solution that we are going to obtain, then we generate the first solution, which is in this form. Now, from our previous classes on the special function, gamma, beta, and the factorial function, we have established the meaning of r sub k as factorial function of r into k terms. Some textbooks call this Pochama notation. And don't forget, we define r sub k then as r plus 1, r plus 2, up to r plus k minus 1. That is the definition. The second solution is obtained by substituting 1 minus t into the recurrent solution that will be obtained after solving equation 1 using Frobenius method. And that solution is given as x raised to the power 1 minus t summation k from 0 to infinity r plus 1 minus t sub k s plus 1 minus t sub k divided by 2 minus t sub k factorial x raised to the power k. In hypergeometric function form, we write it as r plus 1 minus t, comma, s plus 1 minus t, semicolon, 2 minus t, semicolon, x. Those are the two solutions we are going to obtain after solving equation 1 using the method of Frobenius. Now, there are some certain things we need to know as far as these two solutions are concerned. Number 1, k factorial must always be preserved. It is a structure and it must be preserved. Number 2 is that the parameters at numerator and denominator outside k factorial must always be written in terms of Pochama notation or in terms of factorial notation. As far as our class is concerned, I'll be using the term factorial notation instead of a Pochama notation. That's how I'll be. They are defined the same way. The definition, the Pochama notation and factorial notation, they mean the same thing. Now, having said this, having looked at the structure, then how do we obtain the two solutions? Let's see how we obtain the two solutions using Frobenius method. Now, let us rewrite the equation 1. X 1 minus x y prime prime plus t minus r plus s plus 1 x y prime minus r s y equals to 0. Call this one equation 1. So by method of Frobenius, we let the trial solution to be a sub n x raised to the power n plus c n from 0 to infinity. That's our trial solution. Call this one equation 2. So we are going to substitute equation 2 into equation 1 using equation 2 in equation 1. Let me quickly do some rough work there before the substitution. If I differentiate, we need to differentiate equation 2 twice because we have second order here and this is the first order. So the first time the derivative becomes a sub n into n plus c x raised to the power n plus c minus 1. Second derivative becomes from 0 to infinity becomes n plus c into n plus c minus 1 a n x raised to the power n plus c minus 2 n from 0 to infinity. So substitute into that equation. X will multiply y prime prime and that becomes summation n from 0 to infinity n plus c into n plus c minus 1 a sub n x raised to the power n plus c minus 1. Because the law of indices, x is multiplying the power of x on the y prime prime and that increases the power to minus 1. Then we have minus x times x multiplied by y prime prime will give us summation n from 0 to infinity n plus c into n plus c minus 1 a n x raised to the power n plus c. Now, t multiplies y prime. So these are y prime. T will multiply y prime to become summation t into n plus c a n x raised to power n plus c minus 1 n from 0 to infinity. The next term is minus r plus s plus 1 multiplies x multiplies y prime. So let x multiply y prime first, since r plus s plus 1 is just a single term and those are the parameters that we have there. By the time that we multiply this, we are going to have r plus s plus 1 summation n plus c a n x raised to power n plus c n from 0 to infinity. Then the last term minus rs summation a n x raised to power n plus c n from 0 to infinity, everything equals 0. That is what we have. Let us be doubly sure here that we have considered all the terms that are needed. Number one, how many terms do we have? 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. There is no term that is left untouched. Then what is the next line of action here? You observe. Look, let us observe the power. We have just two powers. The first power is n plus c minus 1 and the second power is n plus c. Let us collect the same power together under a single summation. Let's start with the smaller power, which is n plus c plus 1. So this implies that I have n from 0 to infinity, n plus c minus 1. There is one common factor, which is n plus c. N plus c is common to the two of them, and the other one we are now left with n plus c plus t minus 1 a n x raised to power n plus c minus 1. Then for the second power, negative, negative, negative. So negative is common to all of them. That was the first one. Secondly, this term and this, they have common factor, and that common factor is n plus c. N plus c, let us open a very big bracket here, n plus c, then this plus this will give us n plus c plus r plus s, then minus rs a n x is power n plus c n from 0 to infinity. Everything equals 0. So we have been able to achieve that purpose. We've been able to write the two power in compact form. We have written the two of them in compact form. So what is the next thing? Now you observe that the counter are the same. However, the powers are not the same. In that case, one of the fundamental things we need to consider when solving using series method, when solving differential equation using series method, is to ensure that the counter of all summations are the same, the powers are also the same. In that case, what we are going to do now is we look at the difference between the two powers. The difference between the two powers is just 1. The difference between n plus c and n plus c minus 1 is 1. So therefore, we are going to shift the counter of the least power by 1. Then we return it again by 1. We shift the counter forward by 1. Then we move it backward again by 1. What do I mean? It simply means that I will evaluate the least power at the first counter, which is n equals to 0. So let us do that and see what the results will be. Now, evaluate x raised to the power n plus c minus 1 at n equals to 0. So I will not want to jump step here. So substitute 0 for n at this point. We have c into c plus t minus 1 a naught x raised to the power c minus 1 plus. So now that we have used the first value of the counter, the next value becomes n equals to 1 n plus c into n plus c plus t minus 1 a n x raised to the power n plus c minus 1 minus summation n plus c plus r plus s minus rs a n x raised to the power n plus c, everything equals 0, n from 0 to infinity. Now, so there is an obstacle. The obstacle now is that the counters are no longer the same. The counter here starts with 1, the counter here starts with 0. We must make them the same. To make them the same, we still move ahead with the least power. Our least power here is n plus c minus 1. I want to make this one to become 0. How do I do that? There is need for transformation here. And how do we undo the transformation? In order to make this one 0, our n need to be n plus 1 equals 1. So that n equals to 0. The implication of this is that for every value of n here, I substitute n plus 1. That will not affect the second summation, but it's going to affect the first summation. So that means that I have c plus t minus 1, a naught, x raised to the power c, plus, since the counter now will shift to 0, we can bring the two of them under the same umbrella by saying n equals to 0 to infinity. This one becomes n plus 1 plus c. This becomes n plus c plus t. A n plus 1 minus, I have this one to be n plus c plus r plus s minus rs. So this is a n, then I have the x is power n plus c, everything is 0. Now we have achieved our aim here. The same counter for all of them and the same power. What next? We equate the coefficient. Equate the coefficient. Let's start with the first term here. We are going to have c into c plus t minus 1, a naught becomes 0. So assume a naught is not 0. Assume a naught is not 0. What does it imply? It implies that I will have c into c plus t minus 1 equals to 0. This is what we refer to as indicial equation. Indicial equation. Solving this equation further implies that I have c equals to 0 and c equals to 1 minus t, which confirms the first note we had at the beginning of the class, that solving using Frobenius, the hypergeometric equation has two roots that are called indicial roots, and the two roots are 0 and 1 minus t. Having obtained that, we will also consider the remaining coefficients. So in the remaining coefficients is the whole of this bracket. That's our coefficient. So we equate that also to 0. We make the a with the highest subscript the subject of the formula, and that gives an plus 1 equals n plus c into n plus c plus r plus s minus rs, all divided by n plus 1 plus c, n plus c plus t, a n, comma, my n start from 0, 1, 2, it continues. This is what we have. So the new equation, let's call this equation 3. Equation 3 is referred to as the recurrence relation for hypergeometric equation. And it is this recurrence relation, that is equation 3, that determines the structure of the solution. How do I mean? We are going to substitute the initial root into equation 3 now. We start with the first one, c equals to 0. We generate the first solution. We go back to equation 3. We substitute c equals to 1 minus t to generate the second solution. So when c equals to 0, equation 3 becomes, what will it become? Equation 3 becomes an plus 1 equals n into n plus r plus s minus rs divided by n plus t into n plus 1 an. So that's what you're going to have. So don't forget that our n starts from 0 upward. Then we substitute 0, we substitute 1. We start looking at the result that is being obtained. Do we have a relationship among the results? If we have relationship among the results, can we generalize the results? If yes, we are going to do all this. If no, we leave the result the way we obtained it. However, before we start the solution, this is factorizing. How will I factorize this? I have rs here, r multiplying s. I have r plus s here. So what I will do now is to multiply n with either r or s here, then combine it. How do I make? I can write that one as n plus r plus ns minus rs. Sorry, n multiplied by this, n multiplied by this, yes. Here I have n into n plus r plus s is common here. S is common here, then I have something is wrong. The term just before this where I collected the negative, I didn't take care of the negative. This is supposed to be plus, this is supposed to be plus. Please, that has to be taken care of. I'm sorry about that. I factor out negative from onset, but I didn't take note of that. So let's continue. Then we have this one to be n into, we have this to be n plus r into s. So the common factor is n plus r, then we have n plus s. So that this becomes n plus r, n plus s divided by n plus t into n plus 1 an. Then what do we do? So we start the substitution. When n equals to 0, I have a1 to be r multiplied by s divided by 1 plus t multiplied by 1 a naught. N equals to 1 implies that I have a2 equals r plus 1 s plus 1 divided by 2 plus t, or t plus 2, then multiply by 2, I have a1. However, there is a value for a1, and that value is r multiplied by s divided by d. So that becomes r into r plus 1 multiplied by s into s plus 1 divided by t plus 1 and t plus 2. No. Substitute 0 here gives ordinary t. Why at this point I have 1 plus t. So I have this one to be t into 1 plus t. Then we have 1 multiplied by 2, a naught. Looking at this, it defines factorial function, and that becomes factorial function of r to 2, factorial function of s to 2, then I have this one t to 2, then 2 factorial a naught. Let us consider more terms, more values of n. I will return equation 3. Now, substitute n equals to 2. What do we have? If I substitute n equals to 2, I have 2 plus r. I have s plus 2. That is a3 divided by t plus 2, 3a2. a2 has value. This is the value I will make use of this. But let us use this so that we'll be able to see the trend. Then we have r plus 1, r plus 2, s plus 1, s plus 2, all divided by t plus 1, t plus 2, 1, 2, 3, a naught, which gives r3 s sub 3 divided by t sub 3, 3 factorial a naught. We can continue on and on until we get to the final term, which will generalize what we have obtained. And the generalization is very simple. It continues until I have, say, ak. And how do we generalize? When it was 1, we have sub 1, sub 1, sub 1, 2, the same thing. Now that we have k, so it is going to be r sub k, s sub k, divided by t sub k, k factorial a naught. So this is generalization when we substitute c equals to 0 as initial root into equation 3. Having obtained the general form of the results, what next? What are we going to do? Very simple and straightforward. What we're going to do now is to go back to our initial trial solution. Recall equation 2, that y is summation a and x is power n plus c, n from 0 to infinity. Now that c equals to 0, put c equals to 0. It implies that I have y equals to summation a n x is power n, n from 0 to infinity. Expand this one. It is a0 plus a1x plus a2x squared plus it continues. We will observe from the result that we obtain that a0 is an arbitrary value. It has no value. a1 has value, a2 has value, a3, a4, and so on, they have value, and their general representation is a sub k, r sub k, s sub k, t sub k, k factorial a0. So what am I trying to say in essence? substitute this value now. We have a0 plus summation k from 1 to infinity r sub k s sub k divided by t sub k k factorial a0 x raised power k. That will be the solution. Now, the next question we need to ask ourselves is it possible to start this counting from 0? If yes, we'll be able to put a0 together into what we have here. Now, how do we know that? We try to substitute a 0 into this, then obtain a0. If we are able to obtain a0, then a0 can actually move into the summation. If not, this becomes the final result. Let's start. Put a 0 here. Of course, the factorial notation against 0 is 1. This is also 1. This is 1. A 0 factorial is 1. Then x raised to power 0 is 1. Law of indices. Then we are left with a0. So that means that the final solution, which is the solution 1, becomes a0 r sub k s sub k divided by t sub k k factorial x to the power k from 0 to infinity, which is written in the form f r comma s semicolon t semicolon x, which is the first solution of hypergeometric equation. And this solution is referred to as hypergeometric function, as explained earlier in the class. I want to believe my viewers are following with the steps that we are taking as far as the solution of hypergeometric equation is concerned. Let us now consider the second solution. To get the second solution, we go back to equation 3. We substitute the second initial root, which is 1 minus t, into equation 3. Then we carry out steps similar to what we used to obtain the first solution. Let's look at that. Sorry. Now, we put c equals to 1 minus t. This implies that our an plus 1 equals n plus 1 minus t into n plus r plus s plus 1 minus t plus rs, all divided by n minus t all divided by c is 1 plus minus, that is n plus 2 minus t into n plus 1. Then we have an. That's what we have. So we also follow the same way. Can we factorize this? Because I have n plus 1 minus t here. I have r multiplying s here. Then I have r plus s here. I can actually use the first bracket to multiply one of r or s. So let me take, in this case, let me take s. The first time we use r, so let's take s here. Minus t into n plus r plus 1 minus t plus s into n plus 1 minus t plus rs. So s is common here, and that gives n plus 1 n plus r plus 1 minus t into s plus n plus 1 minus t n plus r plus 1 minus t. That's what we have. Now n plus r plus 1 minus t is common. Then we have n plus r plus 1 minus t into n plus 1 plus s minus t. And those are the two factors of our numerator. So that an plus 1 becomes n plus r plus 1 minus t into n plus s plus 1 minus t divided by n plus 2 minus t, then n plus 1 an. So that our a1 becomes, substitute 0, we have r plus 1 minus t into s plus 1 minus t divided by 2 minus t, then we have 1, a0. a2 gives r plus 2 minus t, s plus 2 minus t divided by 3 minus t multiplied by 2, a1. a1 has a value already, and this is the value, so we substitute. Then we have r plus 1 minus t into r plus 2 minus t of